Imagine you are halfway to the moon.
Okay.
You're sitting in this incredible multi-billion-dollar spaceship, just hurtling through a vacuum at thousands of miles an hour.
Right. The pinnacle of human engineering.
Exactly. And yet your biggest, most urgent crisis for the day, it's a frozen toilet pipe.
Yeah, that really, it completely shatters that hyper-polished, kind of sterile sci-fi illusion of space travel we usually have in our heads.
It really does. And that grounded reality is exactly what we were getting into today. We're taking a deep dive into the raw communication logs and the actual video transcripts from NASA Johnson during Artemis II.
Specifically focusing on Flight Day 4. Right?
Yes, Flight Day 4. Our mission for this deep dive is to basically extract the unvarnished reality of deep space travel from these raw sources. Because, it turns out it's not just about majestic, sweeping views of the galaxy.
Oh, definitely not.
It's about the gritty, brilliant, and honestly sometimes hilarious problem solving that happens when you are 168,000 miles from home.
Yeah, I mean, when you strip away the polished press releases and just listen to the raw chatter between mission control and the crew, you get a completely different texture of what it means to be an astronaut.
Totally.
You hear the actual friction between, theoretical engineering and the very messy reality of human biology.
Right. So whether you listening right now are a total space fanatic or you're just someone curious about how humans handle incredibly high-stakes problem solving, this deep dive is going to give you an unfiltered look at how humanity actually navigates the ultimate frontier.
It's a fascinating day to look at.
It really is. So let's set the scene for Flight Day 4. The Orion spacecraft is out there. They are 168,000 miles from Earth.
And about 110,000 miles away from the moon.
Exactly. And the first big piece of news from Mission Control is actually what they are not doing. The outbound trajectory correction burn, or OTC-2, was officially canceled.
Which is, that's a massive engineering triumph.
Really, just canceling a burn is a big deal.
Oh, absolutely, because in orbital mechanics, an initial engine burn near Earth has to be flawlessly precise.
Right.
Even a microscopic fraction of a degree in error, it magnifies over 250,000 miles.
Oh, wow. So you'd end up missing your target entirely.
Exactly. So
Okay.
canceling OTC-2 means their initial trans-lunar injection, that's the massive engine burn that threw them out of Earth's orbit back on Flight Day 2, it was so perfectly executed that they didn't even need a secondary course correction.
That's just wild. So because they skipped this major rocket burn, the crew suddenly finds themselves with, well, the most precious and rare resource in spaceflight.
Free time.
Free time.
Yeah.
And how do they spend that saved time? They use it to troubleshoot the Universal Waste Management System.
Which is NASA's multisyllabic way of saying the toilet.
Right, the toilet. Pragmatism at its finest.
Yeah. Before you can sit back and philosophize about the cosmos, you really have to make sure the plumbing works.
You really do. So here's the situation with the plumbing. The night before, there was a scheduled wastewater dump to clear the tank. But it failed after venting only 3% of the liquid.
Just 3%.
Yeah, 3%. So now the wastewater tank is sitting at 64% full. The hard limit is 80%, and they still have a long way to go before they get home.
That's a tense situation.
Definitely. So Mission Control instructs the crew to use backup collection devices overnight, just in case.
Which really highlights the absolute necessity of engineering redundancy.
Right.
In an environment that hostile, you never just have one way to do something critical. You build a primary system, a secondary system, and then, you have literal backup bags for the most basic human needs.
Backup bags in a billion-dollar ship. I love it. But the fix for this primary system is where the environmental ingenuity really shows.
It's so clever.
Right. Mission Control hypothesizes that the primary vent nozzle on the outside of the ship is simply blocked by frozen liquid. So they crank up the internal heaters on the nozzle and the lines.
But they go a step further.
They do. They actually physically reorient the entire Orion spacecraft. They tilt this massive vehicle just to point that specific vent nozzle directly at the sun.
They are leveraging the ambient environment of deep space because, we always think of space as cold.
It's freezing cold.
Right. But it is also flooded with intense, unfiltered solar radiation. Without an atmosphere to scatter those rays, the sun acts as an incredibly powerful thermal tool.
It's basically a giant heat gun.
Exactly. Instead of draining their internal batteries to run the heaters harder, they use that ambient solar radiation to bake the ice out of the vent line.
That is so cool. But of course, every solution in space seems to introduce a new variable.
Always.
Because of this new angle, the sun is now beaming directly into the cabin windows, absolutely blinding the crew,
And a normal person would think, just pull down the window shades.
obviously. But Mission Control specifically asks the crew to physically remove the window shades.
Yeah, and that's because the thermodynamics in a vacuum make pulling the shades down a structural hazard.
Wait, really? A structural hazard?
Yeah. Down here on Earth, if you pull a blind down over a sunny window, the air in the room circulates. Warm air rises, cool air replaces it.
Right, just basic convection.
Exactly, that convection naturally cools the glass. But in the Orion capsule, the air doesn't naturally circulate like that. If those shades are pulled down while the unfiltered sun is hitting them, the heat gets trapped in the tiny gap between the shade and the window glass.
Oh, man.
The windows themselves could overheat, which introduces a severe structural constraint risk to the spacecraft's hull.
So they have to take the shades off.
They have to.
The cabin gets overwhelmingly bright, the multi-million-dollar glass is protected, but the astronauts still can't see.
No, they're completely blinded.
And their high-tech solution to this thermodynamics problem is, wait for it, a t-shirt.
A literal t-shirt.
They literally use what the logs call a makeshift t-shirt to block the light on window 1. I mean, let's unpack this. It's basically like taking an RV on a cross-country road trip, realizing the wastewater pipe is frozen and having to park the RV at a very specific angle so the sun melts the ice.
Except you're doing it in a vacuum, and you've taped a t-shirt to the windshield.
Exactly. Is that juxtaposition of extreme high-tech and, like, ultimate low-tech surprising to you?
Honestly, no. It is the defining characteristic of human spaceflight.
Really?
Yeah. I mean, what's fascinating here is that you can engineer the most sophisticated vessel in history, mapping out trajectory nodes and thermal limits, but at the end of the day, you have biological humans inside dealing with biological realities.
True.
Progress is never just about perfect equations. True problem solving is always going to be a mix of high-level intellect and practical, messy workarounds.
Messy workarounds, for sure. And dealing with biological realities doesn't stop at the plumbing, either.
Not at all.
NASA knows the human body is the most fragile system on the ship. Which brings us to another fascinating task they tackle while hurtling through the void.
The Avatar payload.
Yes, AVATAR, which stands for Virtual Astronaut Tissue Analog Response.
This is a profound leap in predictive medicine. The Avatar payload is organ-on-a-chip technology, and it's packed into a device about the size of a standard USB thumb drive.
A thumb drive.
Yeah, it's incredibly small.
And inside this thumb drive are actual living cells developed from pre-flight blood donations given by this specific crew.
Which is mind-blowing.
It is. But how does a USB drive keep human cells alive and measure them in the middle of space?
Well, the chip features microscopic, microfluidic channels that constantly pump liquid nutrients to the cells.
Okay.
So it's effectively mimicking a human bloodstream. And as the ambient radiation and microgravity interact with the chip, sensors inside the chip read the specific cellular distress signal.
So it's constantly gathering data.
Right, they're monitoring gene expression and protein markers in real time.
So the AVATAR payload is basically sending a microscopic biological stunt double into space alongside you.
That's a great way to put it, yeah.
You've got your actual body floating in the cabin, and then a tiny chip version of your cells floating right next to it, experiencing the exact same environment.
And that stunt double allows scientists to isolate variables.
How so?
By comparing the chip's data with findings from the International Space Station, as well as the actual crew's bodies before and after the flight, they can map out exactly how deep space stressors degrade human tissue.
Ah, I see.
If we can validate that these chips accurately predict a biological response, we can send them on uncrewed missions to test radiation shielding from Mars.
Oh, wow.
Yeah, without ever risking a human life.
That is incredible. But the human element of this mission isn't just biological, it's deeply psychological. And that takes center stage during a live interview the crew conducts with NBC's Tom Costello.
The farthest interview in history since 1972.
Over 50 years since a human voice was broadcast live from that deep in the cosmos. And the geometric perspective they described to Costello is just mind-bending.
It really is.
They are looking out the window, and they see the Earth in almost full eclipse.
Yeah.
But then they look at the moon, and it is in almost full daylight.
Yeah, to experience that specific lighting contrast, a darkened Earth and a fully illuminated moon simultaneously requires an incredibly specific physical placement.
Right, because usually we see it the other way around.
Exactly. You have to be located exactly halfway between the two celestial bodies, with the sun hitting the moon squarely from your vantage point, while the Earth is silhouetted against the sun's glare.
It's a visual geometry literally impossible to witness from the surface of the Earth.
You literally have to be in deep space to see it.
And staring at that dark, distant Earth triggers a very deep psychological shift. One of the astronauts reflects on the fact that they're heading into Easter Sunday.
Right.
And looking at this impartially, exactly as it was stated in the logs, the astronaut remarks that whether you celebrate it or not, whether you believe in God or not, looking back at Earth from that distance is an opportunity to remember that we are the same thing and that we got to get through this together.
It's powerful. And this is actually a well-documented psychological phenomenon known as the overview effect.
The overview effect.
Yes. When a human brain, which evolved to understand local territories and arbitrary borders, is suddenly suspended in the blackness of space and sees the entire Earth as a single, fragile, interconnected system.
The cognitive boundaries just dissolve.
Exactly. The physical distance forces a recalibration of scale, emphasizing human unity over earthly divisions. Hearing it articulated live, from the midpoint between two worlds, carries an incredible weight.
It really does. And they took a brief moment of stillness to capture that unity, taking a quote-unquote family portrait.
Oh, yeah.
The whole crew gathered in the windows, and Mission Control used the cameras out on the solar array, the saws, to snap a picture looking back at the ship.
A great moment.
But that stillness doesn't last long, does it?
Now, back to work.
Right, because after posing for the camera, they have to physically wrestle with the momentum of this massive ship. Canadian astronaut Jeremy Hansen and NASA astronaut Christina Koch swap seats to test how Orion handles manual piloting before they reach lunar orbit.
Yeah, they run the spacecraft through two specific handling modes, comparing 6 degrees of freedom versus 3 degrees of freedom.
Okay, so in a car, we basically just have 2 degrees of freedom.
Right.
We can move forward and backward, and we can turn left and right. So how does 6 actually map out when you're flying in a complete void?
Well, you break it down into two categories, translational and rotational. The 3 translational movements are sliding your position without turning. That means thrusting forward or backward, sliding up or down, and sliding left or right.
So just moving along the axis.
Exactly.
Yeah.
Then the 3 rotational movements change where the nose is pointing. You have pitch, which points the nose up or down. You have yaw, which turns the nose left or right. And you have roll, which spins the spacecraft along its long axis, kind of like a drill bit.
Like a drill bit. Got it. So as they test these incredibly precise maneuvers, they notice some mechanical quirks.
Yeah, a few issues pop up.
First, there is some play in the orb mount, the actual physical controller mechanism. But the really tricky part is what the engineers call cross-coupling from the rotational hand controller.
Right, cross-coupling.
The crew reports that when they tried to execute a simple 20-degree yaw, just turning the nose 20 degrees to the side, they accidentally induced 4 degrees of roll at the same time.
Unintentionally spinning the ship.
Yeah, and later the vehicle overshot its target heading by 7 degrees before the automated system slowly tried to correct it. So if I turn the steering wheel of my car, it doesn't also tilt my car sideways. Why is steering a spaceship so messy?
It's a great question, and it comes down to physics. The cross-coupling is a direct result of thruster placement and shifting mass.
Shifting mass.
Yeah. When you steer a car, friction between the tires and the asphalt keeps your movement predictable, but in a vacuum, there is zero friction.
None at all.
To turn the nose of the spacecraft, you fire tiny reaction control thrusters on the outside of the hull. But Orion's center of mass is incredibly complex, and it's constantly shifting as fuel is consumed.
Because the fuel tanks are emptying.
Exactly. If the thrust vector isn't perfectly aligned with that changing center of gravity, pushing the nose to the side will naturally introduce a slight, unintended rotational spin.
So the ship just kind of wobbles into a roll.
Essentially, yes.
And what about that overshoot?
Yeah.
If you're firing a thruster and there's no friction to stop you, that 7-degree overshoot isn't an error in the steering wheel, right? It's just Newton's first law playing out in a vacuum.
Precisely. An object in motion stays in motion.
Right.
On Earth, air resistance naturally slows you down when you take your foot off the gas. In space, if you fire a thruster to start turning left, you will keep turning left forever until you actively fire an opposing thruster to counter that momentum.
You have to literally hit the brakes with another rocket.
Yes. And if that opposing thruster fires a microsecond late or isn't quite strong enough to cancel the rotational energy perfectly, you overshoot your target by 7 degrees.
Man, so they have to actively fight their own momentum.
Constantly.
And understanding these handling quirks now seems vital before they get anywhere near another object.
Oh, absolutely. If we connect this to the bigger picture, right now they are in open space, so a 7-degree overshoot is just a data point.
Just a learning moment.
Right. But on future Artemis missions, they will be executing precision docking maneuvers with lunar landers or the Gateway Station.
Oh, wow. Yeah.
In a docking scenario, a 7-degree drift isn't just an engineering quirk, it is a catastrophic collision risk.
That is terrifying.
They have to know exactly how the ship's center of mass handles before they attempt those incredibly fine movements.
And steering the ship requires total precision, especially because of how fast they're approaching their destination.
They're moving incredibly fast.
The logs note they are gaining 1 mile of distance from Earth every single second.
A mile a second.
They are currently 151,476 nautical miles from Earth, and they are pulling out the 400-millimeter camera lens to observe the moon. Because Flight Day 6 is going to be their closest approach, their flyby.
It's coming up fast.
And astronaut Victor Glover is described as being absolutely mesmerized, and Christina Cox states, "It is not the moon you see from Earth whatsoever."
The view must be staggering. They are seeing specific lunar features in rich, three-dimensional detail that we simply cannot perceive from the ground.
What exactly do they see?
They call out Merimbrium, noting its distinct high albedo ring, and albedo is just the measure of how reflective the surface is.
Okay, so a really bright ring.
Right. They spot the massive basin of Mare Oriental and the highly distinct crater rays of Tycho and Copernicus,
Oh, wow.
alongside the magnetic anomaly of Rainer Gamma.
Wait, let me stop you there. Christina Cox said it's not the moon we see from Earth, but we're looking at the exact same object.
Oh.
We can see those same craters and those same dark spots with a decent telescope from our backyards. What physical difference does distance actually make if they're still just looking at the same giant rock?
Well, it really comes down to atmospheric distortion and the angle of illumination.
The angle.
Yeah. When we look at the moon from Earth, we are looking through miles of turbulent atmospheric gas, which bends the light and flattens the image. Furthermore, when the moon looks brightest to us, a full moon, the sun is positioned behind the Earth, shining directly onto the moon's face.
Oh, I see. It's like shining a stadium spotlight directly at someone's face. It just
Right.
washes out all their features.
Exactly. But when you move that light to the side, suddenly you see the shadows of their nose and cheekbones.
That makes so much sense.
That is the exact mechanism at play. Out there, the crew is looking at the terminator line, which is the dividing line between day and night on the lunar surface.
The edge of the shadow.
Right. Along that edge, the sun is hitting the surface at an extremely severe low angle. Without an atmosphere to scatter the sunlight, the contrast between the illuminated peaks and the pitch-black valleys is absolute.
No twilight, just pure light and dark.
Yes, it casts massive, incredibly deep shadows that reveal the true height of the mountain ranges and the staggering depth of the craters.
Wow.
Suddenly, the moon isn't a flat, glowing disk in the sky. It is a heavily battered, fully 3D world floating right in front of them.
They can literally see the topography rising up along the far western edge. The visual shift must be breathtaking, and it is accompanied by a major philosophical milestone in the mission logs.
The reference shift.
Yes, they officially request to change their altitude reference display. Up until this moment, their instruments measured their altitude relative to Earth.
Right? How far they've traveled from home?
Mission Control gives the go-ahead, they flip the switch, and they change the reference point. They are now officially 76,362 nautical miles from the moon.
The moon is now their primary anchor.
It is a quiet operational procedure in the logs, but it signifies the psychological and mathematical transition from leaving home to arriving at a new destination.
Yeah, that's a huge moment.
It really is. When we synthesize this entire day, Artemis II Flight Day 4 is an absolute masterclass in the realities of space exploration.
A study in contrasts, really.
Completely. I mean, in the span of a few hours, humanity's finest explorers are thawing out a frozen wasteland using unfiltered solar radiation.
With a t-shirt on the window.
With a t-shirt on the window, they're testing the limits of human biology on a microfluidic USB drive.
Right.
They are wrestling with Newton's laws of motion to steer a spaceship, and they are staring out the window at the staggering 3D topography of the moon.
The greatest takeaway here, for me at least, is what it tells us about progress.
What do you mean?
Well, the grandeur of spaceflight doesn't erase the mundane physical realities of life. It just puts them on a grander, more hostile stage. It requires an incredible adaptability, acknowledging that true problem-solving always requires both high-level theoretical intellect and practical, sometimes very messy workarounds.
Progress isn't just perfect equation.
Exactly. It's adaptability.
We started this deep dive thinking about the sheer contrast of being halfway to the moon while dealing with a frozen toilet pipe. And it leaves me with one final thought to ponder, inspired by that very last detail we discussed.
The reference point change.
Exactly. The crew flipped a switch and mathematically changed their instrument reference from Earth to the moon. As we look toward the future, when human beings eventually build permanent bases on the lunar surface, at what exact point in that 240,000-mile journey will those future travelers stop thinking of Earth as down and start calling the moon home?